Because the equation for torque is that torque equals the force times the displacement from the moment arm times the sine of theta. We're going to say that the torque on that stick is equal to the force applied there times the distance from the moment arm times the sine of theta.
Why is it sine of theta?
We don't use it, right?
That's exactly, yeah. We don't use it because when we look at our free body diagram, if we had a force, if we had a force coming off not perpendicularly, this would be our angle. However, since these forces are applied perpendicularly, because when you shoot,
It's like going like this.
you're pushing, as you're trying to get the most amount of force. When you generate the most amount of force out of your hand as long as you push straight through the stick and straight away from the stick, and pull away from the stick. So we say this is perpendicular, so the angle is, actually it's not 0, it's 90 degrees, which is why it equals 0. So the sine of 90 equals 1, so this will just cancel out. So now we're just saying that that force applied times that distance. Now, we know that the forces, since it's the same person shooting, is always going to be the same. So we can say that the relationship between the distance and the torque applied to the top of the stick are directly related, which means that as the distance increases, torque will increase. So that's the relationship between these two. So that's why when you have a longer stick, the distance between where it rotates around, the top of the stick, and on the longer stick, since this is greater over here, you're going to get a larger amount of torque, or you're going to get a larger amount of force, which will increase the torque up here at the top of the stick. This right here, the torque right here,
It's supposed to be 0?
it's not 0, but what it is a big fat ass question mark.
So we don't want to use that in our equations or anything?
Yeah, we don't want to use it in our equations. We just want to find the sums of the torque. I'm really excited. So what we're trying to find, sorry. So we have to find the sums of the torques. And this one is unknown. So what we do is we make our moment arm. And we say, if we put it there, you're like, Ian, you put it there, and you're just assuming, you're assuming that you know more about this torque than you actually do. And I'll be like, touche, bitch.
So this is actually our unknown. We don't know this.
So
we have to change up
Okay,
our moment arm?
Thank you for correcting me, because now what I realize is that this torque right here, or this force right here, are two unknowns. But you assume that the force on the left hand and the force on the right hand is the same. We can measure that because we have Chris here. We can't measure this, so we're going to have to assume that we need to solve for that eventually. But for now, we need to find the sums of the torque on this entire stick. So now what we have to do is we have to change our equation.
in the center. That dot is wrong, right? Isn't the center?
It should be moved up here.
It should be moved,
Right?
Exactly. So
Yeah.
that's the moment arm. And what we need to do now is we can use the moment arm to eliminate a torque that we don't know. So we could redraw our free body diagram so that it looks something like this. And we can turn it to even make it easier. So this is the top of the stick here. This is the torque of the shot. So this is the top. That's what we want to know. This can be the bottom hand, which will have that force, and this will be the top hand, which will have that force. We assume the forces applied are equal, but the torques will still be different, since the distance from the moment arm is different than, or they're not the same. There you go. So we place our moment arm there. This distance is going to equal something, which we can measure in a minute, and this distance right here is going to equal something else. So to find the total distance, we can just add these two together. Sorry, this is going to be easier. Now what we have to do is we have to find the sums of our torque. The sum of the torque is going to equal the torque at the top of the stick, the torque of the right hand and the torque of the left hand. Exactly. So we take our sums of our torques. This is going to equal, once again, torque at the top of the stick plus the torque of the left hand plus the torque of the right hand. We take our general equation, which is that torque equals the force times the distance from moment arm times the sine of theta.
Theta is equal to 1, so that.
Exactly. Our sine of theta, each one of these forces is perpendicular to the lacrosse stick. So we say that sine of 90 is equal to 1. So this will essentially cancel out of our equation in all situations.
That's convenient.
It is very convenient. So now we can just say that the torque is equal to the force times the distance from the moment arm.
Distance being the total of D1 and D2.
For this one, now we can write it out. So the sums of our torques, sums of our torques is now going to equal the torque of the stick, which from right here is going to equal some force that we don't know, so that is an unknown, times the distance from the moment arm, which is equal to 0, times 1, which is the sine of theta. We can now take the torque of the left hand, which is equal to the force applied by the left hand, which is also equal to the force applied by the right hand, unless for some reason Chris or I has been abnormally working on one side of our body. I don't know why we do. It's that force times, we'll just say the force of a hand, times the distance from the moment arm, which is D1 in this situation. We now add that to the last force, which is the force of the hand again, times the distance plus D2, so D1 plus D2.
Why is it plus?
Because we're trying to find this whole distance right here.
Hey, what was that question again?
Sorry, ask it again.
Why is D1 plus, why do you add D1 plus D2?
We add D1
Okay.
plus D2 because, sorry, hold on, we can do it like this.
Because you want the torque of
Because
the
it's so
whole
so
thing.
weird, she asked the question and I get a magic line there. So ask it again.
Okay, so why are you adding D1 plus D2?
We add D1 plus D2 because we need to find the total distance from the moment. If this is our moment arm, and this is the force we're trying to find, we need to sum the entire distance, and we only know the 2 seconds. So it's this distance of D1 plus this distance of D2. Now you can come back in here and say that since this is equal to 0, the sums of the torques is actually only going to equal the force of a hand times D1 plus D1 plus D2. And we can actually, ooh, sorry, that's wrong. I need parentheses and asking what the force. So the force of the hand plus, parentheses, D1
Why is it?
plus D2. It is times. I'm wrong again. Alright. Now we can
Good
actually
thing we have them here.
factor out the force of the hand. So we can say that it's the force equal to the force of the hand times T1 plus T1 plus T2. And that's our final equation. Sorry, one more parenthesis. That's our final equation for the sums of the torques. So we write that equation over here. So,
So we plug in.
sum of the torques is equal to
So this is just for the long.
this is just for the long stick. So sorry, this is the sum of the torque on the long one.
255.
And that's Newton meter. What are the units? Newton meters? What's the units for torque? It'd be newtons.
Times meter, yeah, Newton meters.
Okay. So the sums of the torque for the long pole is equal to, what was it?
255.
200. What's over here? 5.
Newton meters.
And that comes out to 129.
129 newton meters,
Mhm.
almost half, or about half. Damn.
Almost, yeah, double. So it's like about 1.98 times greater.
1.98 times greater.
Mm-hmm.
So the distance, and we can say the sums of the torque in these situations is equal to 255 newton meters and 129 newton meters.
So that kind of proves what you guys said in the beginning, that the long stick has a greater force.
Yeah, just by putting the moment arm where the ball is, the torque around that moment arm is almost double